Hey everyone, how's it going? I have very little feedback this side, so I guess we'll just kick off into it. I'm really sorry I couldn't make it. Would have been really great to see you all, but the world is what it is, so we continue. So this is the sun. And the sun's a massive ball of burning hydrogen. It's a fusion reactor that pumps heat and light and energy out into the solar system, and it helps keep the Earth and all of us alive. And over the next kind of 5 billion years, it's going to run out of all of its fuel and start burning helium, at which point it will start to grow and grow and grow, eventually turning into what's called a red giant. And over the next several billion years after that, it will grow so large that will eventually engulf Mercury and then Venus, and then most likely it will consume the Earth. Incremental growth can have a really big impact over a long period of time. Tiny little changes, tiny fractions of a percentage growth each year will add up over the years and eventually destroy the entire planet that we call home. It's simultaneously incredible, but also kind of terrifying to think about. And quite frankly, there's enough terrifying stuff going on right now. So how about we just chill for a little bit and talk about computers? But first, the usual spiel about me. So I'm Craig, and much like the sun, I'm a super hot giant ball of existential terror. And I come from a small town called Whanganui in Aotearoa, New Zealand, but right now I live in Stockholm in Sweden. Like many of you, I have the privilege of writing software to earn a living, and my day job is working on the desktop app and the web player at Spotify. Outside of that, I'm also a GDE for Angular, so hi React people. But I really love the web, and I really love helping teams build better software. I'm on the internet, so obviously feel free to reach out. And if you want to grab these slides, you can just scan this QR code and follow along if you want. So far over my career, I've worked for a bunch of different companies and worked on like a number of quite large and old code bases, though obviously those are relative terms. But I've also been lucky to work in environments where the kind of ideas of incremental change were espoused, like always trying to ship working software and making things grow. I've worked in systems that are capable of pretty amazing experimentation and to try to understand the impact of changes and get lots of user feedback. But even with all that, I've still been involved in multiple big confrontational UI rollouts where there wasn't really any going back. So no matter how much you think it's the right thing to do, incremental change is really hard. But maybe a little bit more specifically, dealing with legacy software is hard. And legacy code bases are usually the victim of these incremental changes over time because code bases naturally evolve as priorities change and teams change and technologies change. But a mature system is actually really powerful because there's significant benefits to a status quo. You can't underestimate the value of stable software, like software that had years and years of real users, years of bug fixes, years of engineering time. And it's pretty clear that, billion-dollar companies often exist on top of old code, a prototype that became productionized or a big monolith or something that they couldn't break apart. And these legacy systems are often quite stable until you try to change it, and then everything breaks. And if it's hard to change a system, then it's hard to change bugs, and it's hard to deliver new value. So sometimes you get to a point where the system's not actually stable, it's just in a kind of gradual decay. And you have to ask what the system might look like in 6 weeks or 6 months or 6 years. Sometimes a code base can end up in a state where it cannot be safely changed without making something worse. You've optimized for some paradigm and reached what is known as a local maximum. A coworker once referred to our code base as being in a state of accidental immutability. No matter what we did, something broke. There wasn't a safe path from where we were to where we wanted to be. Most of us have some idea of what we want our code base to look like, and we can imagine some beautiful utopian state that exists, but it might be out of reach entirely. The team has priorities, you have to keep shipping, so dangerous changes happen. It gets harder to make those changes, everything slows down, and eventually what was an engineering problem is now an everyone problem. And maybe eventually someone says, why don't we rewrite the whole thing? And rewrites are exciting. It's kind of revolutionary, right? Like people trying out bold new ideas, everything happening quickly, lots of progress, really, really quick. And you can move fast and you can break everyone's stuff and build hopefully newer, shinier things. And sometimes revolutions are necessary. Sometimes a system is so broken that the best path through is to burn it all down and start again and hope that you do end up with something better. But they can also be dangerous and lots of people can get caught up in the middle. With software particularly, there are so many cautionary tales of change where it's all gone wrong. We always think it'll be different for us. But in my experience, it usually involves scope creep and too many things changing at once. You may end up through the other side, but there's always a cost. Maybe that's just time and money, but people can be affected by these big changes as well. At a minimum, if you're not careful, you can lose institutional knowledge, tiny implementation details for edge cases or important tests, or even just, commit history comments, those kind of things. So what are the options other than a full burn it all down revolution? Maybe the best way to change a system is from within the existing system. So instead of a full rewrite, maybe it's better to try to make things better within the existing code base and take on the pain of that local maximum. You can start a new branch and start working your way on a fix. This is a tried and true approach for smaller changes, but what about for huge bits of technical debt? Some debt is so coupled to the rest of the code that you can't just fix it bit by bit. And often it's so compounded that it's hard to find the time to pay it all off at once. It's also very hard to quantify and therefore hard to prioritize. So you have some tech debt branch, but it might exist for a long time, just slowly being worked away on whenever it's possible. But then that branch diverges from the made code base and merging gets harder and harder. And along with the technical challenge, you've now got a communication problem because other people continue doing things in some old way. You might try to communicate that to the team with like a lint rule or something, but you've got hundreds of errors. And so you disable the rule everywhere that it fails, or maybe just make it a warning and then everybody ignores it. Either way, the decay continues. Sometimes it's possible to automate a change, which can reduce the pain of that communication breakdown. And some things can't be completely automated, but maybe you can get 90% of the way and then tidy up the last few things. But despite all that, there are, of course, a large number of these kind of changes that computers just can't do yet. Humans are currently still the winners when it comes to like creative or subjective things. A computer can find all the uses of an old API, but it can't necessarily tell you which new shiny API you should use to replace it. It's quite common to have to do migrations like this that are quite hard to automate, especially when there's UI involved. So how do we break these problems down into something that can be dealt with more easily? Let's think about buttons for a second. Pretty much every application has them, and lots of them. And it's not uncommon for them to be implemented something like this, where just different classes are used to change the color. This is totally fine, but it falls apart a little bit when you think about like theming your application. Say if you're going to introduce a dark mode. Instead of describing your buttons by what color they are, you might want to describe your buttons by the semantic function of the button, like what the button does, not how it looks. So you might want to change your buttons, the classes on your buttons, to something like this. I've worked in multiple design systems that have gone through this exact migration, and maybe you've seen it too. The challenge here is that there isn't a direct one-to-one mapping from color to semantic meaning, so it really can't be automated. In the worst case, you might have to go through every single button and decide how to migrate it. Chances are you're going to have some messy in-between state where you might have multiple button implementations in your code base, lint rules, deprecation notices, the whole thing. And you have to put in an effort to make the migration happen. So how do we actually approach this? How would a human migrate all these buttons? So say we've got 100 buttons in our application. You'd find the first button and sit down with the designer and figure out some rules to decide what sort of button it should be. Does it designate a positive action or a destructive action or something else? You update the code for that specific button, and now you're 1% done. You've got 99 buttons to go. Sounds pretty straightforward, but the hard part here is what applying the rules means. It's another communication problem. You need to be able to specify the exact justification for why a button might have one semantic meaning over another. And that kind of nuance is really hard to express to another computer, to another human, let alone a computer. So it's hard to automate. So how do we break this down? How do we break down these rules? How do we come up with some kind of heuristic decision-based way to communicate what we're trying to achieve? What ultimately it comes down to is that humans are actually pretty good at breaking down problems. If you break down a big problem into a set of smaller problems, they can be easy to solve individually. You may have some problems combining the solutions, but that's just another problem, which again, you can break down and solve. There's been a continuous movement towards building software in this kind of way too. Microservice architectures have become more popular than big monolithic applications. Each part of the system can be considered separately, can be changed separately without impacting the whole. Similarly, with component architectures and front-end code, smaller components are easier to reason about and change. These architectures put a large emphasis on how each small part communicates with each other, so that as long as you don't break the contract or the API, the implementation can change how it needs to, independent from other components. Of course, this architecture doesn't come without a cost. You might have new ownership problems or composition problems or just API design problems. But the fact remains that building systems in this way allows for change to happen in smaller chunks and for the system to evolve over time. There's actually a whole category of algorithms for finding solutions via evolution. So an evolutionary algorithm is just an algorithm that explores solutions to a problem using a heuristic inspired by natural evolution. These algorithms reflect the process of natural selection where the fittest individuals are the most likely to successfully reproduce to the next generation of solutions. One specific type is called a genetic algorithm. And there are two key inputs into a genetic algorithm. The first input is a genetic representation of potential solutions to the problem. Each variable in the solution is called a gene, and a bunch of genes combine into a chromosome, which represents one solution to the problem. A number of solutions are then collected together into a population. To solve a problem with a genetic algorithm, you have to decompose the problem into all the variables that might impact the solution in order to determine what each gene should be. The second input is a fitness function, which takes a chromosome from the population as an input and then evaluates the fitness score of the solution. Each chromosome in a population is evaluated by the fitness function so that each chromosome has a fitness score. Once the fitness scores of the whole population has been evaluated, the selection phase begins. First, solutions are sorted by their fitness scores, and some number of weak or low scoring solutions are terminated. Then there's a crossover phase, which determines how many genes should be shared between the parent chromosomes. And then they're combined to make new chromosomes to have a full population again. Finally, there's some small number of genes within the population that get mutated. And then the fitness phase all starts again. So you run the test and run the scores again. And then you select based on the new population. This should tend towards a good, but not necessarily optimal solution to the problem. It's entirely possible for these genetic algorithms to also end up at a local maximum. So let's explore how we might decompose a problem so that it can be used with a genetic algorithm by thinking about Tetris. When we play Tetris, our brains are constantly applying a set of rules for whatever we might think is the best strategy for getting a high score. We might try to clear lines wherever is possible, or try to save up lines so that we can clear 4 at a time. But we have to decide how to place the shapes in order to clear lines. So maybe we want to always have as many sides of the current block touching the bottom as possible, or have as many blocks touching other blocks. Maybe we just want to not introduce any holes. Each of these variables for playing the game can be a gene in a chromosome that describes the solution. The fitness function for Tetris is just playing the game with these kind of heuristic rules and then seeing what the score is. So here's an example where I've implemented exactly those rules into a genetic algorithm for playing Tetris. Each chromosome has 10 genes, where each gene is a variable that impacts the strategy for Tetris. The initial population has just random values, but the fitness function plays the game with those weightings, and then over time, it slowly gets better. At first, it really sucks at playing Tetris, but over a series of generations, the chromosomes become better and better, quickly becoming much better than me. By decomposing a problem like this, we can describe the game of Tetris in a way that allows for incremental improvement over time. So, wouldn't it be great to have a way to describe a change that you want to make in your codebase and define what incremental progress towards that final state looks like? We know what our codebase looks like now, and we know what we want it to look like in the future. So we need a way to break down the difference between those two states into smaller pieces that can be dealt with incrementally. We need a way to break down our code into quantifiable, countable pieces, much like the chromosome in a genetic algorithm. We need a fitness function that takes a codebase and produces a score. But it actually turns out that there are many ways to represent our codebase. We just need to think about our code as data. Let's look at this little bit of code. What different types of data can we get from it? First, there's the actual code that runs the program. From this, we can see that this function is asynchronous, it's got an argument, it has a call to a constructor in it. But then there's also dependency information about how files relate to each other and how they use third-party dependencies. There's also some little bit of documentation in the comments, which might have higher level information than the actual code. This is TypeScript, so there's also type information about how data flows through the program. We can use various tools to read our codebase and quantify it in all kinds of different ways. We could count the number of files with a certain extension, or count up circular dependencies, or compiler errors. By quantifying these things, we can break down the problem from one thing that needs fixing into individual small things that can be fixed independently. But that's not some new idea, right? It's maybe a slightly different way of thinking about it, but that's what TypeScript or ESLint or Jest or any other number of tools already do. We can think of TypeScript as a fitness function, or ESLint, or any tool that we can think of that can quantify our codebase. What we need is a way to compare the quantified state of the codebase between two different points in time. So let's say we start out with our main branch and run some fitness function like TypeScript or ESLint over the codebase to get some representation of the current state of the code. And then we have some work done in a new branch with some changes to the codebase. We can run the fitness function again on the new branch to get the new state of the code. What we really need to define is a comparison function to assess the difference between these two states. The comparison function has the job of working out if the new state is better than the old state, worse than the old state, or the same as the old state. A comparison function like this acts as a constraint, trying to guide your codebase in the right direction towards being better. So that means that the result of the fitness function can actually be anything you like, as long as you can compare the results. But changing branches all the time kind of is a bit tedious. You don't want to have to do that. So is there a better way to keep track of the current state of the main branch? It's actually become pretty common to store extra information about a codebase inside the codebase. So chances are, if you're working on front end, that somewhere in your codebase, you've got a dependency lock file, or maybe a Jest snapshot file, or even an actual image file if you're doing visual regression testing. We could use the same idea and maybe store the current quantified state of the codebase inside the codebase. This adds one extra constraint to the fitness function. The result has to be serializable, but that means that we can compare the current state to the last committed state. And so with that, we actually have the three little pieces we need to enable a gradual incremental migration in a situation where automation just isn't feasible. So we need a fitness function that takes our codebase and turns it into a quantified, serializable representation of the state of the codebase. We need a comparison function that takes two representations and determines if one is better than the other, worse than the other, or the same as the other. And we need a mechanism for reading and writing results from disks so that they can be stored in source control and compared between branches, kind of like a JS snapshot file. And I've been working on wrapping this idea up in a little tool. And I've been calling it Betterer. Betterer is a tool designed to make incremental improvement easier. You can think of Betterer kind of like a test runner, like Jest or Mocha, but the difference is that a Betterer test starts out as broken by default. A Betterer test is a way to communicate your intention to other developers that there's something you want to improve in the code base without the need for disabled lint rules or long-lived branches and without needing to burn everything down to start again. You can check out the docs online, but let's just dive in and see how it works. You can start off by running the initialization script. That just sets up a few things in the code base, adds some dependencies, and gives us some scripts that we can use to run Betterer. And the initialization script also creates us a new Betterer config file, which is basically the entry point to your tests. Straight out of the box, that's actually enough for Betterer to start doing its thing. Of course, right now it does nothing since we haven't defined any tests, but let's fix that. So what should a test do? The test is a fitness function for our code base. So it can be basically anything that you want, as long as you can represent the result in some way to be compared. As an example, I have a project that I want to convert from JavaScript to TypeScript. So let's write a test that just counts the number of JavaScript files in a code base. First, we're just going to go to that Betterer file, import Betterer test, and then define a new test called migrate.js to TS. Now we just need to write our test function. So this is the actual function that scores the fitness of the code base. For now, we're simply going to use the glob library and count up the number of files with the JS extension. A number is nice and easy to compare, and it's also serializable, so that's good. Now we just need a constraint function, which does the comparison. We're going to pull in constraint result and return better if the new result is smaller than the expected result. So if we have fewer JavaScript files, the same if we've got the same number of JavaScript files, or worse if we have more JavaScript files. Of course, comparing numbers is pretty common, so we can just import smaller. In this case, if something gets smaller, it's getting better. You might also use bigger for some tests. Now, if we run Betterer again, we're going to see something slightly more interesting. We can see that our test migrate JavaScript to TypeScript got checked for the first time, which is great. But what did this do since we had nothing to compare it against? Since we don't have an existing result, Betterer just runs the test and takes what it gets as the base state, serializes the result and stores it in this new file, the Betterer results file. In this case, we're just saying that there are currently 9 JavaScript files in the codebase. This is the thing that's basically the same as the JS snapshot file. So now we can run Betterer again, and this time we'll see that the result is the same. We didn't change anything, and Betterer found the old results file and used that as a comparison point. So this is fine. Nothing got worse, we haven't gone backwards. And that's basically our first test working. So we've got everything set up, and along comes a friendly neighborhood engineering manager, and they're adding a new feature, and they haven't heard about our plan to migrate to TypeScript yet. So they add a new JavaScript file to the project, and when they try to commit, they run Betterer, and they get a big error, and they can't move forward. That's good for the state of our code base, but maybe it doesn't quite communicate what's going on as well as it could. So let's change a few things to communicate more clearly. While our initial approach was fine, it's actually pretty common to want to have a test that targets specific file types in your code base. And Betterer provides a pretty easy way to do that by using a file test. The way you create a file test is a little bit differently. It just takes a function with 2 parameters, file paths and file test result. Betterer can actually be quite smart, and sometimes it'll just pass you a subset of files, like if you're in watch mode or if you're only running against the files that have changed since the last commit. The file test result is just a container that we use to tell Betterer about objects in a file. We can use this include method to tell Betterer that we only care about JavaScript files. So that's just going to pick any JavaScript files in our code base, but it will exclude anything that's been excluded from source control. The body of this test is again pretty simple. Since the include glob only targets JavaScript files, we just need to create an issue for every file that the test receives. To do that, we can just read the contents of the file with the fs module, and then call add file on the file test result object. We then add an issue to the file and pass the position of the issue. 0 and 1 is simply going to attach the issue to the first character of the file, and we give it a nice, helpful error message. And now we run the test again, and it's actually much better. We're going to get a whole bunch more detail about what's going on. Get a nice little code snippet and the error message, and we get the warning that we should use TypeScript. But because we used the better file test, we've still got 9 files found that were JavaScript, but there's a lot more detail in the results file. Better serializes this to contain information about where the issues are in your codebase, so that if they move within a file, or even if a file is renamed, these issues can still be tracked. Now with that updated, we can commit and merge the updated test, and our engineering manager can update their branch. As an added bonus, and for even faster feedback, we could get our engineering manager to install the VS Code extension so they can get these errors in the editor as they make changes. But now, because our engineering manager only gets like 15 minutes a week to actually code, they don't have time to fix the JavaScript right now. But that's okay, because they can just use the update flag to force Betterer to update the results file, just like with Jest. This means they can move on and make a pull request. Because the results file is committed to the code, hopefully someone will still pick it up in a code review and maybe challenge them on that decision. But sometimes you have to make things a little bit worse so you can continue to move forward. But it really should be a last result. In that case, Betterer will update the results file, and now we can see that we have 10 total issues. So the results file matches the state of the code base again. So Betterer is going to go back to reporting that the test is the same, and now we're back to a stable code base. And even though they couldn't help out this time, our engineering manager loves this idea. So they know we have to get this migration done. The team can discuss a date when they want to meet the goal by, and they can set a deadline for the test. Once the expiration date passed, nothing really happens. Betterer just gets a little bit more shouty about fixing things. And so now the team's agreed to prioritize the migration. Other team members can dedicate some time to fixing up the issues in small chunks. Someone comes along and they decide to migrate the file that the engineering manager added, as well as one more for good measure. They run Betterer again, and it reports that 2 issues were fixed. Now we're even better than we were before. Things got better, so Betterer updates the results file, cementing in the new, healthier state of the codebase. If the JavaScript files would change back, Betterer is going to report that the test is worse again and the build will fail. So there's a lot of things you can apply this idea to. We could write a test for TypeScript if we wanted to enable a stricter compilation mode. Or we could use some linting tools like ESLint or StyleLint to introduce new lint rules. Or even just track simple to-do comments with a regex matcher. It doesn't have to be JavaScript. We could even use this tool on things like Kotlin, as long as it's a serializable result. We could migrate from old React class components to function components, or enable stricter type checking in templates in Angular, or we could check accessibility violations with Axe, or even test code coverage with Jest. There's a ton of possibilities. Betterer gives you quite a lot of power in how you define tests and how you measure test progress. But since these tests are just functions, it's actually pretty easy to just wrap the power into a module. These modules can then be shared or reused. Betterer actually comes with a few built in to help you get started. I'm sure more will come in the future. Okay, so that's Betterer. If you can't tell, I'm super excited by this idea. I've been working on it for more than a year now, and I still haven't lost any interest. But if this is exciting to you as well, and you'd like to help me out, please hit me up. We're probably not going to stop the Earth from being swallowed by the sun, but we might be able to make some stuff a little bit better. Thanks so much, everyone. Feel free to hit me up online if you have any questions. Enjoy the conference. I really, really wish I was there. Thanks, and have a good day.
Thank you very much, Greg.